Okay, in this section we're going to focus on how we go about recognizing patterns. And before we begin, what I want you to do is take a look at the screen and tell me what it is that you see. All of you should immediately recognize and be able to tell me that that is a letter A. You can also probably tell me there's a capitalized version of the letter A. And this is something we can do without any conscious effort, so we're not needing to think about it really. It just automatically pops out that that's a letter A. What about now? If you look at the characters that's on the screen, if you are familiar with Mandarin, you'd probably quite easily recognize that this is the number 5. Again, it would just sort of pop out. Whereas if you're not familiar with Chinese characters, then this probably won't mean very much to you. You'll just look at it. You might have an idea that it is a Chinese character, but beyond that, it's just going to be a collection of vertical and horizontal lines that are appearing there. So the question in this section of the lecture is, how do we do this? How do we end up taking particularly 2D stimuli or 2D images and turning this into a representation that we can understand and link to some knowledge that is stored in memory? So how do we store conceptual knowledge of 2 lines that go up like that with a crossbar across, represent the letter A, and that the Chinese character represents the concept of 5? So pattern recognition is basically this cognitive process that allows us to identify and categorize regularities in the environment. So this can extend to letters, numbers, outlines, figures, any sort of shape. So as long as we can discern the edge of it, it's going to involve some degree of pattern recognition to identify it. For example, how do we know that this collection of 3 lines, so 2 lines that point up towards each other and meet at the top, and then 1 horizontal crossbar, how do you know that that collection of lines is the letter A? How, from seeing that particular pattern, do you access this concept of A in your brain? And there's 2 different approaches that have been proposed for how we might go about doing this. One of these is known as template theory. So it might be the case that we store templates for all of the possible patterns that we might encounter, or we could match according to features. So let's go through, have a look at the difference between these. So according to template theory, this is suggesting that we end up storing in our brain a really large set of templates. So a template would be a highly detailed model for patterns that we've previously encountered and that we might come across in the future and might recognize. And then if we want to recognize a stimuli that we're looking at, what we do is take that visual input and compare it to all of the different sets of templates that we have stored in our memory, and we select and choose the template that is the closest match to the stimuli that we're looking at. So patterns are then recognized based on which template has the closest match to the stimulus, and then we would decide that yes, that template that is stored with this conceptual understanding that it's the letter A, that's the closest one to this stimulus that we're looking at now, that's it. So a kind of very rough illustration of how this might work is that if you see this stimuli, you're looking at the grumpy cat, and you pick out the kind of edge features of this cat, and then you would compare that to all of the stored representations that you have that are similar to this. So you might search through a template of one form of cat, yeah, not close, not quite that one though. You look at the next one, it's a dog. Yeah, not that one. And then you come across this template that does provide the closest possible match to the stimuli that you're looking at. And you would decide, yes, that stimuli that I'm looking at is closest to this template that I have. It must be this concept of the grumpy cat. So alongside these templates being stored, they would also be linked to the knowledge of what this template represents. In this case, grumpy cat. However, there's a bunch of reasons why template theory doesn't necessarily seem appropriate or plausible in all situations. So 3 main criticisms that come with this is, firstly, variation. There's too much variation in visual stimuli that might match the same template. So if only an exact match would do, what we need to do is store templates for every possible configuration or font that a letter is presented in. So if you were to think about storing a template for the letter A, what would that template look like? How would you construct it? Could you create one that you would then be able to compare and match all possible variations of the way that the letter A is presented? Well, that seems challenging. So if we look at on the slide here, if you look at the different ways that the letter A can be presented, there's a huge amount of variability in the different designs and formations of how this can be presented. Yet when you look at each of these, you can still, with relative ease, recognize every single one of them for being the letter A. Some may be more tricky than others. And for template theory, this really sort of places a challenge on what you would need to do in terms of creating a template. Because it seems challenging if you could have one template that represents all of these letter A's. So the alternative argument is that maybe if we wanted to go along with template theory, we create separate templates that represent every single possible form or way that that letter A could be presented. Now the challenge for this, again, is that you can recognize letter A's that appear on there in a font, in a style that you have never encountered before. So effectively they're kind of novel letters that you're looking at, yet you're still able to detect the pattern that's there and recognize it as being the letter A. So another challenge for template theory here is that we're very capable of easily recognizing patterns when they appear at a different orientation. So if the letter A is kind of on its side or at 45 degrees, and if it's a different size, so whether it's large or small, we can easily understand what the pattern is. Now, this presents a bit of complexity for how template theory would actually go about dealing with this. And the question then is whether you would need multiple different templates for each concept. So for the letter A, would you need to store templates that are all possible different orientations and at different sizes? And again, as we said in problem 1, with different variations. And this leads to just a big problem of the amount of complexity that would be involved. So this would be a highly inefficient way. And one thing that we'll get to know about the brain is that it likes to be as miserly and as lazy as possible. So it generally likes to find efficient solutions for solving problems like this. Now the counter argument to this is you could say that maybe there is some sort of normalization process that goes on in visual processing where whatever stimuli we see, we end up rotating it maybe to the proper orientation. We represent it at a kind of typical standardized size, and then we engage in some sort of recognition process. So that's one way we could get around it. But I think the general conclusion with template theory is, at its strictest form, the concept of the idea of having templates that represent every possible configuration of stimuli that's out there is unwieldy and unlikely. So an alternative theory for how we go about recognizing patterns was proposed by feature matching theories, and this argues that a pattern consists of a set of specific features or attributes. So for example, if we look at the letter A again, this is represented by 2 straight lines that head up in sort of just a little bit steeper than a 45-degree angle that are connected by a horizontal crossbar that goes across. So it's not that we store a template, but we store the principles of what key features there should be for this particular pattern. So in this case, we're storing two horizontal lines and a connected crossbar, and everything that shares or has, every stimuli that has these properties, we would interpret as being the letter A. Now the great advantage of doing this is that then the stimuli can vary by its size, its shape, its orientation, but it's still going to be effectively identified by these kind of core features, and it's still going to be correctly matched to that representation that you have stored in memory. So one nice example of a kind of feature matching model is Oliver Selfridge's pandemonium model. And this was essentially a very early attempt to try and understand how individuals could process letter recognition. So it was using computer simulations of how this might occur. And this model became famous for a couple of reasons. The first one is that as scientists started to learn more about how individual neurons in the brain function, and particularly in the primate brain, they started to realize that this pandemonium model and the way it's described very closely mimics the way that the primate and the human brain operates. And secondly, the other reason for it becoming famous is that Selfridge described the model in a pretty entertaining way, using these metaphorical demons that each have specific functions or duties to analyze different features of the stimulus, and doing this in a hierarchical manner. Okay, so in this model, the image demons receive a retinal image and pass it on to feature demons. So the image demon is kind of like just doing basic sensory processing. So they're passing on this signal that's received in the retina. So in this case, we've got the image of the letter R that's being presented. Now, after this information has been passed on, each feature demon calls out when there are matches between the stimulus and the given feature. So for each set of feature demons, you can think of these as the equivalent of being a set of neurons that get really excited and enthusiastic when there's particular features present in the image. So we have some neurons that get really excited when they see a vertical line, some that get excited by horizontal lines, some that get excited by diagonals, and others that might get excited by curves. So whenever a feature demon notices one of these, they're activated and they're kind of shouting out this information. And these matches are then yelled out at demons at the next level of the hierarchy, which known as the cognitive or thinking demons. And the cognitive demons then in turn shout out possible patterns that are stored in memory that conform to one or more of the features noticed by the featured demons. So in this case we have D, P and R are all possible combinations based on the individual feature demons that are excited and activated. These could all represent the overall pattern of being the letter D, P or R. You then have a decision demon that listens to the pandemonium of the cognitive demons, and it decides on what has been seen based on which cognitive demon is shouting the most frequently. So whichever one has the kind of most matches or is being the most excited. So out of this, we then have the decision demon is basically selecting that yes, the letter R is the most likely letter that we're processing here. So again, this whole thing is occurring automatically. So let's have a look at a kind of applied example of this in a bit of an interactive. So in this interactive, which I'll share the link with you, you can have a play around and see how these feature and cognitive demons and decision demons feed up signals to each other based on different input. So at the moment we've got our feature demons down here that are snoozing away. Everyone's snoozing, there's no inputs they're receiving right now. What we can do is give them some visual input. So if we give them this image that they're going to appear, so we've got two vertical lines and a horizontal here, which is pretty straightforward. It leads to a high degree of excitement of these two feature demons, and then in turn this leads to a little bit of excitement for the cognitive demons A. So he's essentially on the lookout for the horizontal here. That's what wakes him up a little bit and gets him excited, but not too excited. Similarly with the R, he's getting a bit excited about this vertical bar that we've got of the feature demon. But the most excited, enthusiastic is the cognitive demon for the letter H. So it's a pretty easy decision here for the decision demon that can tell you, yeah, this is the most strongly activated cognitive demon. Now, I've already sort of alluded to one of the other advantages of the feature matching theory, which is the fact that you get corresponding evidence that comes from studying the activity in single neurons of particularly the visual cortex of the cat, but also of other primates, that you have a very similar process that occurs where individual cells are hierarchically organized in terms of responding to individual features or collections of features. So this was some seminal work that was really done by David Hubel and Torsten Wiesel. Now, Hubel and Wiesel used single-cell recording in the occipital cortex of cats. So what they were doing here is putting electrodes that would go down and could measure the firing rate of individual neurons in the visual cortex. So the research showed that the visual cortex contained specific neurons that respond only to a particular kind of stimuli. So for example, a horizontal line or a vertical line. And these are known as simple cells, and they would also only respond if that stimulus fell onto a specific region of the retina. So there would be a single cell that would respond, for example, to a horizontal line that appears in the upper right region of the visual field, for example. And there'd be another neuron that would respond to a horizontal line that appears in the lower left visual field. So this is one of the real sort of striking discoveries that ended up getting them the Nobel Prize for this. So most of the cells in the cortex don't respond simply to spots of light. Rather, they respond to specifically oriented line segments. So whether that's horizontal, vertical, or some would respond to a diagonal. And these cells then seem to show a kind of hierarchical structure in the degree of complexity of what they would respond to. So something very similar to what we've just described in the pandemonium model. And then higher up in the hierarchy of processing, we can also have complex cells that will respond to particular combinations of features that are independent of the location that they appear in the visual field. Okay, let's take a look at a video that shows Hubel and Wiesel doing their original work on understanding visual processing cats. So what you're going to see in this, and you might need to pay attention closely, but there's a moment when they pull a slide, so a glass-coloured slide, just slightly across the screen, and you then see this spike of activity in the neurons.
The researchers actually listened in to individual nerve cells firing in the anesthetized cat as they presented it with different visual images.
When we started working, Torsten and I, in the late 50s, we set up our first experiments, and they didn't go well because at the beginning we couldn't make the cells fire at all. We'd shine lights all over the screen, and nothing seemed to work. And rather by accident, one day, we were shining small spots, either white spots or black spots, onto the screen, and we found that the black dot seemed to be working in a way that at first we couldn't understand until we found that it was the process of slipping the piece of glass.
So one of the things that's hard to pick up, but if you look at, is this little line that's going across here that is causing activation in the neurons. One of the things, that sound that you hear in the background, one of the ways that they can monitor or notice feedback of neurons firing It's basically you've got a single cell recording device that goes down into the visual cortex, and then every time those neurons fire, that signal is passed to an amplifier that's then connected to a speaker. So every time you hear that little sound in the background, that is the sound of a neuron that's firing. So let's just play that a little bit again as you hear the sound.
Screen, and we found that the black dot seemed to be working in a way that at first we couldn't understand until we found that it was the process of slipping the piece of glass into the projector, which swept a line, a very faint, precise, narrow line across the retina, and every time we did that we'd get a response.
Now, an issue that we come across that is relevant for both feature matching and template theories is this idea that both of them only ever try to account for or explain the way that we process patterns from a bottom-up approach. So bottom-up processing refers to the analysis of the stimulus that emphasizes the characteristics of the stimulus rather than internal concepts, where sensory receptors register information about the environment and send signals upwards. So in other words, we're processing stuff based on just the raw sensory input, so no contribution of our expectations or knowledge. Whereas top-down processing is information processing that's guided by higher level mental processes as we construct perceptions, drawing on our experience and expectations, so the context that we're in, particular schema, expectations that we have, and we're filling gaps in our perception to fit these expectations. So in the context of us seeing a visual stimuli or some kind of pattern, none of these models account for how our interpretation of those patterns might differ depending on the particular context or expectations and biases that we have. But we know that from experimental studies that these expectations that we have can often drive and influence the way that we interpret particular patterns. So our expectations can influence it through priming effects. We'll come on to an example of this in a minute. An example that I think is easy to understand is imagine trying to proofread your own writing. So when you've just written an essay, it's an important essay that you're about to submit and hand in. You're very familiar with what you've written on the page. When you read it through yourself, you have strong expectations and knowledge of the sentence structure, what you're trying to say at each point. And as you read through that, because you have an expectation of what comes next, we can very easily end up missing any typos or errors that were in the writing, just because as you read through, you're sort of predicting what words are going to come up next as you're reading it. So unless you read through word by word or use particular techniques, we often miss our own errors. There's often effects of the context, and we'll come on to something called the word superiority effect. And then at times our mood state that we're in, so whether we're in a happy or negative mood, our experience, biases, etc. can all influence the way we process. Let's look at a couple of specific examples though. So one that we can illustrate the impact of the context is these two lines. So if you read this going vertically downwards, so read what's written here starting with 12, then most of you should read 13, 14. The context that you're in, that visual stimuli that's in the middle, makes sense to be the number 13. It goes after 12 and precedes 14. Makes absolute perfect sense, and as you read that, most people would naturally perceive that to be the case. Whereas if you read going across horizontally, most people would again read that as being A, B, C. So the B in the middle makes most sense when it's in the context of being sandwiched between the C. So in some ways, what you end up doing here is taking that exact same visual stimuli, that exact same pattern that is in the middle, and interpreting it in two different ways depending on the context that's surrounding it. Another example, if you read out the speech by Martin Luther King that's written here, just take a moment to read through the lines. You can read it out loud or read it to yourself. So again, we have an expectation of what it is we're going to read. And this is something that may not work for all of you, and perhaps the case that you're more alert and attentive for these kinds of tricks now that I've already shown you some of the sort of illusions at the start. But what this shows is a clear bias of a top-down expectation of what words we're expecting and not expecting to appear or to be repeated. So you'll notice if you look at this carefully and you read it out, most people would say, I have a dream that one day this nation will rise up and live out of the true meaning of its creed. We hold these truths to be self-evident that all men are created equal. That's what it appears to be when you read it out. But when you actually read it word for word, it's I have a dream that one day this nation will rise up and live out the true meaning of its creed. We hold these truths to be self-evident that all men are created equal. It's very different. But our expectations can mean that we often ignore that repeated filler word that's in there. Similarly, read this sentence. Most people read this as Paris in the spring. Hopefully, after that last example, you might have noticed that it says Paris in the spring. Okay, what about another example? So this is a cat with a bow tie. What does the writing say on the right-hand side? Again, illustrates the effect of context. So the middle letters that appear in both of these words are ambiguous. So if we're thinking about what pattern can we match this to, we've got the two vertical bars that are going up, there's a horizontal crossbar, but it's ambiguous of whether you perceive that as a slightly ill-formed A or a slightly ill-formed letter H. So we've got ambiguity between the two of these. But notice again that perceptually, in terms of the visual stimuli that you're seeing, these two are exactly the same bits of visual stimuli, but you interpret them entirely differently. If you read that as the cat, we're interpreting it as an H in the top word and an A in the bottom word. So again, our interpretation of the context of what letter would it most make sense for this combination of patterns to represent. So it makes sense that it's an H at the top, and it makes sense that it's an A at the bottom. So that's one way that we use our expectations. Another nice example is if we see some work that's done on the effects of priming and interpretation of visual stimuli. So if you look at this again as a ambiguous stimuli image here, if I told you that you're looking at a Native American, so for example like an old statue of a Native American, then many of you would be able to perceive that yes, we've got the nose that's on the left hand side, you've got the kind of dark black hair that's whisked back, and the very strong chin line. What if I told you instead that what you're looking at is an Eskimo? You may have had an entirely different impression of this. So you could see these two different images that appear within that. So the Eskimo on the left, the Indian on the right hand side. And again, you get very strong effects here. If you prime people with these words prior to seeing this image, there's a strong preference for interpreting that visual stimuli to represent either the Eskimo or the Indian. So again, I'll repeat myself, people would be looking at exactly the same stimuli, so that exact same image, but depending on what you've been told in advance is totally, fundamentally influencing the way that you perceive and interpret that same visual stimuli. So one more example here. If you look at the image, I think most of you would see this as a face of a person that's wearing glasses. If I had told you instead that what you're going to see is the word liar written at a sort of 45-degree angle, I'm pretty sure that is the thing that you would have seen first, and you wouldn't have noticed the face. I think the face is the stronger of the two images out of these. But if you're given that knowledge that it's the word liar in elaborate handwriting at an angle, that is what you will perceive. Okay, a final example that I think nicely illustrates some sort of paradoxical influence of the context is a phenomenon known as the word superiority effect. And this is basically the finding that people have better recognition of letters when they're presented within a word as opposed to when they're presented either on their own or presented in a non-word. So let's understand what goes on in this experiment. So if you remember, the way that an experiment is represented is to show them using these grey boxes as what appears at different time points in the experiment. So on the left-hand side, one condition of the experiment, you present a fixation cross in the middle, and then they present a single letter on the screen. So in this case, the letter E is going to be flashed up very briefly. So it's long enough for you just about to perceive it, but not much longer. And then immediately afterwards, you're given a forced choice decision of did you see the letter E or was it the letter T? So in that case, the correct response would be, yeah, I saw the letter E. Now, intuitively, you would think that would be the easiest possible condition that you're doing. You have the least number of patterns, the least number of things to focus on. You should be best in this condition. Now, they then do two other conditions where they present a non-word such as claim and then ask you at the end, in this particular location, did you see the letter E or the letter T? People then are about 65% accuracy of getting the correct one. Sorry, in the first condition where you're just doing the single letter, average accuracy rate is around about 60%. The interesting one is when you then present people, so you flash up an entire word, so in this case the correct word, plain, and then you ask people, in that final letter position, was there an E or a T? Accuracy improves to 80%. So there seems to be some paradoxical benefit here of making it easier when that word is presented within the context. That letter is presented within the context of an entire word. Okay, let's have a look at a real-life case of where our top-down expectations or biases might influence and affect very low-level perceptual processes. So one clip I'm going to show you here is taken from a documentary that is looking at some of these issues in expert fingerprint identification. So when we're doing a fingerprint ID, it's very different to kind of what you might see on CSI of putting something into a computer and definitely getting a 100% match of this is the suspect's fingerprints and this is the fingerprint we've got at the crime scene. It requires a bit more of a subjective judgment. So sometimes you might not have the entire fingerprint that's there, it might be a little bit smudged, etc. So what we've got to do as a fingerprint identification expert is detect patterns of ridges and valleys. So that's all we're doing is comparing what is the pattern on here with the pattern on our other sample. But we find that some contextual information can influence behavior and decision making. And in the case of the fingerprint ID, it can really make a big difference if you know the level of guilt or innocence of the person who you're matching the fingerprint with. So if you're looking at somebody and you're told that this is the suspect and they've been found guilty for the case, there's evidence that that might influence whether you find it more likely that there is a match between the fingerprint that you have and the one that's on the kind of case file. So, for example, in one study, they found that fingerprint examiners were more likely to find a fingerprint match after learning that the suspect had confessed and admitted their guilt to the crime. Conversely, the examiners viewing the same fingerprints were less likely to find a match when they were told that the suspect was in police custody at the time of the crime. So, if you think he's definitely guilty versus we're not sure, he's a suspect, but innocent until proven guilty, it's making a difference on people's judgments. Further, you find if the forensic laboratory requires that a second examiner verifies a positive first matches from the first, you have a problem here in that the second examiner, when they're reviewing this match, they already know that somebody else before them has found that it's been a positive identification there. So it's giving them a very strong prior expectation that they should find a match. And you find this kind of bias occurs towards judging the comparison to be a match. And there's also evidence to suggest that this bias is likely to be stronger and greater if you feel like the person that's already examined and confirmed they're a match, if you think this original examiner is senior and has high credibility, or that there's been multiple examiners that have already confirmed this match before. This information is going to make it more likely that you perceive there to be a match. Okay, let's watch a clip on this. So in this clip, it's going to show a little bit of a documentary where a team have covered the Mayfield case. And this was a kind of infamous case where independent and prosecuting fingerprint identifiers had incorrectly found a match between a suspect and the fingerprint that was found at the scene on the case file. And they argued that they incorrectly found this match because they were unconsciously biased by their expectations that this person was guilty. So let's watch the clip and some of the perspectives from cognitive neuroscience on here.
Running both prints through AFIS.
Unlike fingerprint analysis on television, machines do not make a match. People do.
The examiner is the instrument of analysis. There is no objective criteria. It's a subjective judgment of the fingerprint examiner.
Dr. E.T.L. Dror, a cognitive neuroscientist based in London, is one of the world's leading authorities on fingerprint analysis. He says that examiners can be influenced by bias. We're talking about bias that's unconscious.
Absolutely.
We're not talking about a conscious conspiracy to match up the suspect with the fingerprint.
Absolutely. We're talking about dedicated, hard-working, honest, competent forensic examiners.
Dr. Dror says this is cognitive bias, and in a study to show how strong that bias can be, he took real cases where examiners had found a match, changed the descriptions of the crime, and then asked the same examiners to analyze them again.
I gave the same prints to the same examiner without their knowledge, and a large majority of the examiners said now it's not a match.
So in over half the cases, they would disagree with their former opinion?
Yes, it changed their perception and judgment, and over half said it is not a match.
In the study that Dr. Dror did, the examiners changed their mind. Over half of them.
4 out of 5.
Same data, same examiner?
Mm-hmm.
Same examiner.
Right.
Completely different result. How can that be a science?
Well, there's going to be, I think, variability anytime there's a human involved in the process.
So it sounds like you agree with Dr. Dror when he's talking about cognitive bias.
If you're asking me if I think that there is the potential for cognitive bias to come into play in a fingerprint examination process, I would say yes.
After nearly a century of insisting in and out of court that fingerprint analysis is infallible, the FBI has now changed the way it testifies. Today, particularly since the Mayfield case, you don't testify the way you used to
Right.
testify, right?
Right. I certainly wouldn't say 100% certain or zero error rate. I would want to explain any of those things if I was asked about them.
So there is no infallibility.
I would not testify to that, no.
I think fingerprint evidence is accepted in the United States. I think it is a rare case when they get it wrong. And, you know, the critics can scream all they want, but it's a very vital part of our criminal justice system. He didn't go to jail or anything, though, right?
Scott Burns is the director of the National District Attorneys Association, which represents state and local prosecutors who handle the vast majority of criminal cases.
Nobody ever asked me about the hundreds of thousands of cases every year where it does work and where good forensic scientists testify. We get it right most of the time. The Mayfield case is the anomaly. It is the rare exception. And to hold that up as somehow representative of what goes on in courtrooms across America is just wrong.
What is an anomaly is that they found out, not that they made a mistake. How can he say that you get it right most of the time? How did he know that it's not the tip of the iceberg? To say that Mayfield is an anomaly in a single case is naive at best.
Okay, so in the clip that you saw there, that was just one small section of a longer video that looks at how some of these non-sensory processes, so our expectations and biases, can influence the perceptual processing of fingerprint analysis. So these are experts that are doing their job that you would expect to be impervious or unlikely to be influenced by their expectations and biases, but clearly in the experimental data this seems to be possible. There's something you might pick up on that occurred in that clip that I think is always worth thinking about when we're considering the application of cognitive psychology research, is that there's a lot of tension between findings that cognitive neuroscientists might find and how well this gets accepted in applied domains. So when you look to the responses of a lot of the legal experts that have relied on fingerprint identification for years, they're very reluctant to accept or acknowledge that there may be biases that are coming into play and influencing the accuracy of fingerprint identification. Okay, that's all.